Welcome to my channel. Let's start with the topic concept of internal energy under thermodynamics. So internal energy is actually the internal energy of the system possessed by the system due to molecular motion. One is due to molecular motion and another is due to molecular configuration. So therefore you can conclude that we have two types of energy in internal energy, that is UK and UP. UK is the kinetic energy which is due to the molecular motion and UP is due to the molecular configuration. So the total energy, the total internal energy is denoted by U equal UK plus UP. So this is the formula for total internal energy. In that we have molecular motion, in that we have molecular configuration. We need to take into account both the energies. Now, as you know, we have two types of energy, that is ideal gas and we have real gas. So in the case of ideal gas, as you know, the intermolecular forces are assumed to be zero in the case of ideal gas. So intermolecular forces are zero. So that means there won't be any work done. So if in this case it will be UP equals 0. That means in the case of ideal gas it will be U equals UK. It will be only due to the molecular motion, not due to the molecular configuration in the case of ideal gas. Now, as you know that the intermolecular forces are not zero under real gases, therefore they possess both type of energies, that is due to molecular motion and molecular configuration. So in this case, remember that intermolecular forces are not zero. So therefore we need to take into account molecular motion and molecular configuration. So this is the difference between ideal gas and real gas under internal energy. Now let us move on to the first law of thermodynamics. So first law of thermodynamics says that when some quantity of heat dq is supplied to a system, as you can see here we have a representation of same, dq is supplied to a system capable of doing external work, then the quantity of heat absorbed by the system is equal to the sum of increase in the internal energy of the system, that is represented by du, and due to the rise in temperature and the external work done by the system in expansion. So the energy supplied is equal to energy of the molecular motion, energy of the molecular configuration, and the work done by this system, by thermodynamical system. Now we have some sign convention under this. So first one is dependent on the heat. So if heat is supplied, then dq will be positive when heat is supplied. dq will be negative when heat is drawn from the system. So this is the condition for dq. If you are supplying heat to the system, dq will be taken as positive, and if the heat is withdrawn from the system, then dq will be taken as negative. Now the second one, work done. So it is denoted by dW, and when gas expands, dW is taken as positive. Now when dW is negative, that means gas is compressed. Now the next one is du. So the internal energy. In the case of internal energy, if there won't be any temperature change or the temperature is increased, then du du will be taken as positive when temperature increases. Now du is taken as negative when temperature decreases. So these are the three conditions we need to take into account. Now I am moving on to the applications of the first law of thermodynamics. So applications of first law of thermodynamics has three parts. One is isothermal process, adiabatic process, and cyclic process. So under isothermal process, as you know that the temperature remains constant in this. Temperature is constant. So if temperature is constant, that means internal energy will be same. That is du will be taken as 0. It will be constant again. So under isothermal energy, du will be taken as 0. So my first law of equation will be dq equals dw. So in this case, heat supplied in an isothermal process is used to do work against the external surroundings because it is in positive form. Now the next one is adiabatic process. So in the adiabatic process, as you know that in this case no heat energy enters or leaves the system. As you know it is well insulated. That means in this case dq will be equal to 0 and the first law of thermodynamics will be changed to dq is 0, du plus dw, du equals minus dw. So this means when a gas expands adiabatically, dw is positive, therefore du must be negative, that is internal energy of the system would decrease and the gas will be cooled down in this system. Now the next is cyclic process. So in cyclic process, in this process, the system is returned to its initial state after many number of changes. So it came to initial position. That means in this case, du will be equal to 0. If du will be equal to 0, that means dq is equal to dw according to first law of thermodynamics. So net work done during a cyclic process must exactly equal the amount of heat energy transferred. So that represents cyclic process, which is quite similar to the isothermal process. Thank you for watching this video. We'll continue with the second law of thermodynamics in the next lecture.